Aside from division, our first technique, really the biggest technique in Calculus AB, is substitution. Hopefully you can already do U substitution, for maybe factoring or something like that. We're not going to work on this first objective here. I'll do it a little bit. Eventually, you'll have to choose an appropriate U substitution. The first day tonight's work, I'm going to give you the U's so you can just practice the mechanics of this technique. This is the objective you'll really be doing. You're going to be evaluating indefinite integrals using anti-differentiation by substitution. You can also do definite integrals. We're just not going to focus there today. Eventually, we're going to work on deciding when this substitution is a good technique for doing anti-differentiation. And the short thing is, it's right there. We're going to undo the chain rule. Now, if you're in my classroom, and even if you're watching this, your best bet is to not modify what du is equal to. I don't know. That's something I've noticed over the years. I teach that a little bit differently. And the reason is, you'll see what this means in a second, and I'll come back to it. If you were to rearrange what you have, du is equal to a whole bunch of stuff, you're going to make mistakes. The kids in my class, they're good at the algebra. You guys, but a lot of times you make mistakes. So another way to say this is don't isolate the dx in your work. So just remember, if we said f of u is u cubed and we wanted to do the derivative of f of u with respect to u, we could write d over du of f of u, the derivative of f of u with respect to u, and the derivative of u cubed with respect to u. And so we get f prime of u is 3u squared. I suppose if we wanted to, we could write d something over d something, but that would be du over du, the rate of change of u with respect to the changing u, which is of course just 1, so we don't bother writing that. Now, if we wanted to find the derivative of u cubed with respect to x, our notation would be d over dx, derivative with respect to x. And, no matter what, the derivative of u cubed, or something cubed, is 3 times that same something squared. But in this case, that something is u, which has a rate of change of du dx. You could also say, hey, we're just doing the chain rule or implicit differentiation. Okay. So if g of x is sine of x cubed, what is the derivative of g with respect to x? And on the left-hand side, that's not a big deal. We're just going to say, g prime. Do I have white there? How do I get rid of that? That's super weird. Anyways, so the way I would say it is the derivative of something cubed is 3 times that same something squared. That something is sine of x, which has a rate of change of cosine of x. And so later, we're going to try to undo this chain rule. If you see this, what you're supposed to realize is, oh, the input to this function is sine, and the derivative of sine is cosine. Oh, that's just a chain rule, so I can undo that. Okay, and the derivative, if it's natural log all cubed, that's still kind of the same idea. The derivative of something cubed is 3 times that something squared. That something is natural log of x, which has a rate of change of 1 over x. So again, if we were just going to integrate that right-hand side, ignoring everything else, eventually what you're supposed to see is, oh, this 1 over x, that's actually the derivative of natural log. This is just a remnant of the chain. And last one, again, I keep using the cubing function because it really doesn't matter. Super weird. Anyways, the derivative of something cubed is 3 times that same something squared. That something is cosine, which has a rate of change of negative sign. So in the future, if you see an integral like this with a cosine as an input, you're supposed to realize, oh, this sine, that's the derivative of cosine. And it actually, I kind of say it that way because if there's not a negative, we can take care of that. The hard part is getting the sign there. Okay, so let me show you what that looks like. And this looks impossible to deal with. What the heck is the indefinite integral of 1 over x times 3 natural log of x squared dx? Well, it's clearly not a memorized derivative rule, like if you saw secant squared instead of natural log squared. And you'll see why in a second. We're going to use U substitution to simplify things so you can really see the structure. And so I'm just going to say U is natural log of x. By the end, hopefully you'll see why I choose that. And down here, eventually, we're going to have, if U is natural log of x, we're going to have 3u squared eventually. We want a du. So what we're going to do is find du using differentials. And, du is 1 over x dx. So now, let's bring down some things. We haven't done the integral, that's still there. The 3 is still there. And instead of natural log squared, we're going to replace natural log with u. All right, we have this converter. Wherever you see a natural log, you can write a u. Now again, we want a du. Right here, I'd like to have a du, but I can't just make a du. I need to find some stuff that du is equal to. Well, turns out I need a 1 over x multiplied by a dx to get a du. And if you'll notice, we actually have that up top. So that 1 over x and that dx combine to be that new du that we wanted. So it turns out what we started with is just a chain rule on 3 times something squared. Or at least that's the derivative, because we've gotten rid of that chain rule structure. Anyways, what has the derivative 3u squared if we're treating u like the input variable? U cubed. Don't forget plus a constant. So let's go ahead and put natural log back, and we have natural log of x all cubed plus a constant. And if you think back, we just actually did that derivative recently. What's the derivative of natural log cubed or something cubed? Well, it's 3 times that same something squared. That something is natural log of x, which has a rate of change of 1 over x. Okay, that's exactly what we wanted. So do you see it here? The reason this is a chain rule situation, you always want to look at the inputs. There's this natural log of x right here, and the derivative of that input, that natural log of x, is 1 over x. Oh, that 1 over x is right here. So when we say u is natural log of x, eventually we're going to need a du, so we just find du, and that's 1 over x times dx. So let's go ahead and rearrange. I'm going to bring down my integral and the 3 times my blank squared, but now in my blank, I'm going to write a u, and that x and dx, right, that's the same thing as du, so we replace those with a du. Everything's taken care of. And again, that's a pretty easy antiderivative. What has the derivative 3u squared? U cubed, because we're doing antiderivative with respect to u. So u cubed plus c, and we'll just make that natural log of x cubed. All right, so what if it was squared? Well, not that bad. But now, hopefully what you're seeing is, well, again, u has to be natural log of x, and du is 1 over x dx. So we get u squared du. Pretty easy antiderivative. Okay, here we go. So we're going to start off with something easy. You should be able to find the antiderivative of sine of 4x dx. Of sine of 4x on your own. But let's use U substitution. So I'm going to say u is 4x, which makes du 4 times dx. Now, I know I have the white marker, so I need black or dark blue. Right now, we can rewrite this as the integral of sine of u, but notice this dx here. We want it to be a du. And my rule here that pops out, if u is 4x, du has to be a 4 dx. Well, we don't have a 4, but we need a 4. And this is the thing I'm trying to get you to do to not make mistakes. And can you create a 4? And the answer is yeah, of course. All we have to do is multiply by a 4 and a 1/4, because that's multiplying by 1. And you can always multiply by a constant, 4 over 4, 10 over 10, or something like that, that doesn't change the way you do antiderivatives. So now we're going to be able to rewrite this. The 1/4 is the 1/4. You know, sine of 4x became sine of u, and this 4 in dx became a du. Hopefully that makes sense. And so now we just do a pretty easy antiderivative. The antiderivative of sine of something is negative cosine of that something. Don't forget your plus c, and don't forget to put 4x where u is. All right. So in this case, what I'm about to show you does work, but it doesn't work in all cases, and I'll tell you how and why or whatever. But what I mean by don't modify du is, you know, right here, we had u is 4x, du is 4 times dx, and we need a 4. So a lot of people say, well, just divide so you have dx on its own and make that replacement. And in this case, that totally works. We actually get the integral, right? Because this is the same as 1/4 the integral of sine of u du. That 4 looks like that u looks like a 4. Anyways, the reason I think that's a bad idea, what I've seen over the years is, let's say this was a different case, instead of all of this, if there was a 4 dx there, then people would just divide by that. They wouldn't know what to do, and they'd write a 1 over 4x outside the integral. This is just what I've seen over the years. And so my advice is, don't solve for dx. Don't rearrange this du thing. Okay? In my class, we're going to be silly about it. We're going to make fun of people that do, because they're going to be the ones where they get a quiz back and like, dude, we told you not to do that. And so here's why. You know, this is just kind of the first technique. And if you're doing U substitution wrong, if you choose the wrong U, you're going to make an error. Now, I'm going to read this to you because I think I did a good job typing. If you do that rearranging du stuff, you're going to make errors. You either chose the wrong u, or you're trying to do U substitution when it's not the correct technique. So if you can't do what we did here, multiply by 4 over 4 or 10 over 10 or something like that. By the way, it does have to be a constant over a constant. If you can't do that, we need to try a new tact. Okay? And why does it have to be a constant over a constant? Well, because let's say way back up here. Let's erase this all. If I multiplied by x over x, or maybe something like that, multiplying by x, dividing by x, that creates a quotient rule, a product rule, some sort of weird antiderivative situation that's very different than multiplying or dividing by a constant. Okay, so now hopefully you're getting the hang of this. When we're doing U substitution, we're undoing a chain rule. We're going to see the derivative of this one thing is somewhere else. So the integral of cosine of x times e to the sine of x dx. I'm sure some of you see it, but some people don't. You know, some people see that cosine has the derivative negative sine, and we can deal with negative, and sine has the derivative cosine. So how do we decide which is which? Well, let's just do the work. If u is sine of x, then du is cosine of x dx. If u is cosine of x, then du is negative sine of x dx. Okay. The question is, go back up here in the original integral. Which one is multiplied by dx? The cosine x is multiplied by dx. You know, this sine is locked up inside of the e. So it turns out we can't do u is cosine of x, right? We have to do the one over here, u is sine of x. So e to the power sine becomes e to the power u, and the cosine of x and the dx, those become du. And that's a pretty easy antiderivative. What has the derivative e to the u? With respect to u, well, that's e to the u plus a constant. Or really what we were looking at all along, cosine of x, e to the sine x, that's just the derivative of e to the sine of x. Don't forget your constant, plus c. All right, 2 more. So now the students in my class today were really starting to see this. The integral of 6x squared times the square root of 5 plus 2x cubed dx. And it's hopefully popping out at you. What's the thing that has the derivative 6x squared? And of course, 2x cubed. So if u is 2x cubed, du is 6x squared dx. And we can just rewrite that. The integral comes down. Instead of the square root of 5 plus 2x cubed, the square root of 5 plus u. And the 6x squared in dx, that together became du. But there's a slightly easier way to go. Because there's another thing that has the derivative 6x squared. You know, we can throw that 5 in for free because it's addition. And the derivative of 5 plus 2x cubed is the exact same 6x squared. So in that case, we get what appears to be a little bit simpler. The square root of u is what we're looking for the antiderivative of. And of course, that's the same as u to the 1/2, which has an antiderivative of u to the 3/2. So we'll counteract by multiplying by 2/3 plus a constant. Now in my class, I'm making everybody practice, you know. Sometimes you'll have to rearrange. So instead of leaving this, we can't leave the u, and I'm going to make you practice. U to the 3/2 becomes the square root of 5 plus 2x cubed, all cubed. So just bring everything down. So the last one here is almost the same, but I want to reiterate, let's not change that du. How are we going to deal with this? Because what you should realize is 5 plus 2x cubed still is going to be ru, which means the du that we want, because we want to integrate something with respect to u, we need a du. We need a 6x squared dx. Now the x squared we have, that's actually the easy part. Can we get a 6? We sure can. We are just going to multiply by 6 and multiply by 1/6 at the same time. I'm not going to put that on my original. I used to do that. Now I do it down here. Because hopefully you would agree, well, that 6 times that 1/6 is 1. That's exactly what we have from before. And multiplying by a constant doesn't change the way we do antiderivatives. So now we can rewrite everything in terms of u. The 1/6 comes down. The integral we haven't done. The 6x squared along with the dx become du. And that's the square root of 5 plus 2x cubed, so the square root of u. And again, we just have to do antiderivative of u to the 1/2, 2/3 u to the 3/2. And we'll do a little bit of simplification. 1/6 times 2/3 is 1/9 times the square root. Let's put 5 plus 2x cubed back where the u is. So the square root of that, all cubed, plus a constant. Hope that helps.